Right now, at this exact moment, a machine no larger than a compact car is moving through space that no human-made object has ever entered before. It is travelling at 38,000 miles per hour. It has been travelling continuously at this speed, without slowing, without refueling, without a single human hand on the controls for nearly 5 decades. The nearest star it might someday pass sits 73,000 years ahead at its current velocity. And despite all of that, the distance, the cold, the silence, the permanent dark between the stars, it is still transmitting. Not archived data, not recordings from measurements made decades ago. Live signals produced right now from active instruments detecting things in the sun space between the stars that no scientific model had anticipated. Those signals are crossing a distance so vast that even light itself, the fastest thing in the universe, takes 23 hours to complete the journey in a single direction. 23 hours for a beam of light. That is how far away this machine is, and still it finds things worth reporting home. The spacecraft is Voyager 1. What it is still discovering is not a footnote to a mission that concluded long ago in history books. It is some of the most unexpected science of the 21st century, beamed home at 22 watts of transmitter power, roughly the output of the bulb inside a refrigerator, received by Earth's largest radio antennas after that whisper has spread across 15 billion miles of emptiness and arrived carrying information that is actively rewriting what we thought we knew about the universe directly outside our solar system. Think about that for a moment. 22 watts. The bulb that barely lights the shelf in your refrigerator when you open it late at night is generating as much power as the signal that has crossed the boundary into interstellar space and returned with data no other instrument in existence can provide. The engineers who built this spacecraft in the early 1970s could not have imagined this moment. They did not design it for this. And yet here it is, still functioning, still measuring, still sending its whisper across 15 billion miles of dark. There is a particular kind of vertigo that comes from sitting with this fact long enough to genuinely absorb it. We have sent instruments to every planet in our solar system. We have landed machines on the Moon, on Mars, on Venus, on a comet, on an asteroid, on the frozen surface of Titan. We have flown probes through the clouds of Jupiter and through the rings of Saturn. We have returned images of Pluto's nitrogen glaciers and the geysers erupting from Enceladus. All of those achievements, extraordinary as each one is, took place within the Sun's domain, within the protective magnetic bubble our star inflates around itself through the constant outflow of its own solar wind. Voyager 1 is outside that bubble. It is in the space between star systems. It is moving through the same kind of emptiness that the light from every star you see at night has been crossing for years, decades or centuries on its way to your eyes. From that position, 15 billion miles from Earth in a region no instrument had ever occupied, it is returning data that scientists are still analysing, still debating, and still publishing papers on in peer-reviewed journals. Decades after the original 5-year design lifetime expired. This is the story of what happens when a spacecraft outlasts every expectation, crosses a boundary no machine had ever reached, and keeps finding things the universe was hiding in the dark. It is also the story of the people who have spent careers listening for its signal, the engineers who fixed it from 15 billion miles away, when it began speaking in a language they could not understand, and the scientists who are watching its power supply decline toward the moment when it goes silent forever, while trying to extract every last measurement from the only active observatory humanity has ever placed in interstellar space. The window is closing. The final readings are arriving. What Voyager 1 is still discovering is real, it is important, and it is running out of time. The word interstellar gets used casually enough that it has lost some of its meaning. It sounds like science fiction vocabulary, the kind of language that exists in films and novels, but not in the daily reality of anyone alive today. But Interstellar is exactly what Voyager 1 is, not metaphorically and not approximately. The instrument has physically crossed the boundary that separates our solar system from the space between the stars, and it is physically there right now, measuring what that space is actually like from the inside. That makes this story not a tribute to the engineering achievements of half a century ago. It makes it one of the most consequential ongoing scientific observations happening anywhere on Earth or beyond it, conducted by a team of people at NASA's Jet Propulsion Laboratory who communicate with their spacecraft through a round-trip signal delay of 46 hours and somehow, year after year, decade after decade, continue to make it work. If you enjoy deep dives into real science that completely reshape how you understand the cosmos, hit that like button and subscribe. It genuinely helps this channel grow and means I can keep making journeys like this one. Get yourself comfortable. This story is worth taking slowly. There is a strong tendency to think of Voyager 1 in the past tense. The launch was 1977. The planetary flybys were in the 1970s and 1980s. The famous pale blue dot photograph was taken in 1990. For most people, Voyager 1 belongs to history, a triumph of 20th century engineering that now drifts silently through space like a museum exhibit no one can visit. This framing is entirely understandable. It is also completely wrong. Voyager 1 is not coasting gently. It is not transmitting echoes of old measurements. It is an active scientific observatory returning data about an environment that no scientific model had ever characterized through direct measurement. The discoveries it has made since entering interstellar space, many of them within the last decade, have surprised scientists who devoted entire careers to studying the edge of the solar system. Not in the way that small discrepancies occasionally surprise researchers, but in the deep way where data contradicts theory so fundamentally that theory must be rebuilt from the beginning. To understand why a Voyager 1 is still making discoveries, and why those discoveries carry weight that extends far beyond the prestige of the mission itself, you have to go back to where the story actually starts. Not at the launch in 1977, which is where most tellings begin. You have to go back to a meeting of planetary scientists in the mid-1960s, to a young mathematician with a calculation no one was expecting, and to a window of opportunity so narrow and so cosmically timed that missing it would have meant waiting until the year 2153. The story of Voyager 1 is, at its deepest level, a story about timing. And the timing was almost missed entirely. Gary Flandreau was a graduate student at NASA's Jet Propulsion Laboratory in 1965 when he was assigned what seemed like a routine analytical task. Identify efficient flight paths that future spacecraft might use to visit the outer planets, Jupiter, Saturn, Uranus, and Neptune, in the coming decades. It was the kind of careful, methodical work that could occupy a career without producing anything dramatic. Flandreau performed his calculations and plotted his trajectories across the outer solar system's slow orbital clockwork. And then he noticed something that stopped him completely. The outer planets, the gas giants sitting in the cold dark beyond the asteroid belt, were approaching an alignment that occurs only once every 176 years. Jupiter, Saturn, Uranus and Neptune would all be positioned in roughly the same region of the solar system during the late 1970s and early 1980s. This was not merely an astronomical curiosity, it was an engineering opportunity of almost incomprehensible scale. What the alignment made possible was a gravitational relay, a sequence of slingshot maneuvers using each planet's gravity to accelerate and redirect the spacecraft toward the next. A spacecraft launched at precisely the right moment, aimed at Jupiter on the correct trajectory, could use Jupiter's immense gravitational field to gain velocity and bend its path towards Saturn. Saturn could redirect it toward Uranus, Uranus toward Neptune. A single spacecraft, launched on a single rocket from a single pad in Florida, could visit all 4 outer planets in a single voyage using nothing but planetary gravity as fuel. Without this alignment, a direct trajectory to Neptune alone would require decades of continuous propulsion. With it, the entire outer solar system could be explored in roughly 12 years. Flandreau published his findings in 1966. He called the concept the Grand Tour. The window would open in 1977. If humanity did not launch during that window, the next comparable alignment would not arrive until the year 2153. This was not an opportunity in the ordinary sense of that word. It was a deadline unlike any in the history of scientific exploration. The planets themselves were the clock, counting down toward a window that would remain open for only a few years in the entire span of human civilization. The gravitational geometry that made this mission possible would exist briefly and then close, and no amount of budget, technology, or human determination could recreate that geometry once it was gone. It was set by celestial mechanics operating on timescales that make human planning look fleeting. Either humanity launched during this narrow window, or the mission was simply impossible in any practical sense for nearly 2 centuries. That is an unusual kind of pressure for a scientific program to operate under. A pressure that does not come from politics or budgets or engineering constraints, but from the orbital mechanics of the outer solar system itself. NASA's response to Flandreau's finding was the Voyager program. 2 nearly identical spacecraft, designed at speed and built under real-time pressure, intended to take advantage of a gravitational geometry that nature had been preparing for 1-6 years. Voyager 2 would be launched first on August 20th, 1907, on a trajectory that could allow it to visit all 4 outer planets if the spacecraft survived long enough, and if mission support continued through the 1980s. Voyager 1 would be launched 16 days later on a faster trajectory to Jupiter and Saturn, then directed on a path that would eventually carry it out of the solar system's plane entirely and toward the stars. The 2 spacecraft had meaningfully different futures from the moment of launch, though no one on the morning of either launch knew with certainty that both of those futures would ultimately be realized. The 2 spacecraft trajectories reflected different scientific philosophies built into the program from the start. Voyager 2 was placed on the Grand Tour trajectory, slower but flexible, preserving the option to visit Uranus and Neptune after Saturn if the spacecraft survived and mission support continued into the mid-1980s. Voyager 1 was placed on the faster trajectory optimized for maximum science at Jupiter and Saturn, particularly a high-resolution Titan flyby that planetary scientists had lobbied for intensely. Titan, with its thick nitrogen atmosphere and suspected organic chemistry visible from Earth-based spectroscopy, had been debated among planetary scientists for decades. Whether its surface was covered in liquid ethane, whether its atmosphere contained the amino acid precursor molecules that laboratory chemistry had produced under simulated primitive Earth conditions, whether anything resembling prebiotic chemistry might be occurring on a world kept cold enough by its distance from the Sun to preserve organic complexity, these questions had driven sustained argument for giving one of the 2 spacecraft the closest possible Titan flyby. The argument prevailed. The spacecraft was directed accordingly. The choice carried a clear price. Voyager 1 would not visit Uranus or Neptune. The scientists accepted that price because Titan's implications extended beyond planetary science into the deeper question of whether complex organic chemistry organizes itself predictably whenever conditions allow it, a question whose answer mattered for understanding life's place in the universe. Within the planetary science community, the decision to prioritize Titan's close encounter over additional outer planet visits was not unanimous and remained a subject of debate even after the fact. The argument on the other side was straightforward. Uranus and Neptune had never received a spacecraft visit of any kind. Their atmospheric compositions, interior structures, magnetic field configurations, ring systems, and moon populations were almost entirely unknown from Earth-based observation. The science return from first-ever encounters with 2 entire unexplored planetary systems seemed to some researchers to outweigh the benefits of a closer look at a moon that, however interesting, would at least be observed at some distance by Voyager 2 on its different trajectory. The counter-argument was equally clear. A close Titan flyby could not be duplicated from Voyager 2's trajectory, while dedicated missions could eventually reach Uranus and Neptune. History has shown this argument was right in its specific prediction. The Cassini-Huygens mission eventually explored the Saturn system in extraordinary depth, descending through Titan's haze and revealing hydrocarbon seas, while Uranus and Neptune still await their dedicated orbiters decades later, consistently near the top of priority lists but consistently unable to secure funding. The Voyager 1 trajectory decision, made under time pressure in the early 1970s, shaped the planetary science agenda for the next half-century in ways its authors could not have fully anticipated. The Jet Propulsion Laboratory where these spacecraft were built had been developing deep space probes since the late 1950s and early 60s. The Mariner program had sent probes to Mars, Venus and Mercury. The Pioneer program had already blazed a path to Jupiter. JPL had real expertise but also operated under the specific pressures of the early 1970s, a budget environment tightening as national priorities shifted after Apollo, a persistent awareness that the Soviet Union was running its own deep space program, and a mission timeline that could not slip because the orbital window would not wait. The Voyager spacecraft had to be designed, built, tested, integrated, and launched within a fixed period, regardless of how many technical challenges arose during development. The launch date was non-negotiable in a way that almost no other launch date in the program's history had ever been. The universe had set the deadline, not a program manager. The communication infrastructure that made all of this possible did not exist when Voyager's mission was first conceived and had to be built, expanded, and maintained in parallel with the spacecraft's development. NASA's Deep Space Network, the global array of large dish antennas positioned at Goldstone in California's Mojave Desert, at Canberra in Australia, and at Madrid in Spain, had been under continuous development since the early 60s. When the first planetary missions demanded communications over distances measured in tens and then hundreds of millions of miles, each facility was positioned roughly 120 degrees of longitude from the others, so that as Earth rotated, at least one antenna would always face the relevant region of the sky. The largest antennas serving Voyager during its planetary encounters were 64-meter dishes, expanded later to 70 meters, increasing the receiving area by nearly 20%. Designed specifically for the challenge of recovering coherent signals from spacecraft whose transmitted power was measured in watts, and whose signals arrived after spreading across billions of square miles of space. Every scientific result the Voyager program ever produced passed through this infrastructure. The Great Red Spot images, the ring structure data, the termination shock measurements, the plasma density readings from interstellar space. The Deep Space Network is as integral to the mission's achievements as any component on the spacecraft itself, and its continued maintenance is what makes ongoing contact possible. Building the spacecraft under this pressure required making hundreds of engineering decisions that would remain fixed for the duration of a mission, whose duration, as it turned out, no one could have correctly predicted. The power source was chosen because nothing else could work at those distances. Solar panels at Jupiter's distance receive only 4% of the solar energy available near Earth, making them impractical at any reasonable size, so the radioisotope thermoelectric generators using plutonium-238 heat were the only viable option. The 3.7-meter parabolic high-gain antenna was sized for the data rates needed at the distances of the outer solar system. The 11 science instruments were chosen through arguments among competing scientific teams, each instrument representing a judgment call about where the most important unknowns lay and what measurements would most change the picture of the outer solar system. Every choice was a compromise between scientific ambition and physical constraint, between what could be learned and what could be carried, powered, and operated within the realities of a specific spacecraft launched during a specific year on a specific rocket. Voyager 1 lifted off from Launch Complex 41 at Cape Canaveral on September 5, 1977, atop a Titan IIIe rocket fitted with a Centaur upper stage. The launch was not without anxiety. The mission planners were threading a needle across billions of miles using guidance systems and computing technology that would seem primitive by modern standards, on trajectory calculations of extraordinary precision that had never been tested by actually flying the route. The onboard computers had less processing power than a modern digital wristwatch. The memory available for data storage was a tiny fraction of what any current consumer device holds, and yet the mathematical precision required for the spacecraft to hit its planetary targets at exactly the right angles, at exactly the right moments, across journeys measured in billions of miles, left essentially no room for error anywhere in the chain from design to launch to navigation to encounter. The atmosphere at Cape Canaveral's Launch Complex 41 on September 5, 1977 was shaped by a specific kind of pressure, the understanding held by everyone present who had worked on the mission that what happened in the next few minutes was irreversible in the only direction that mattered. A successful launch could be followed by years of navigation, course corrections, and extended scientific work. A failure with some structural, mechanical, guidance or propulsives could not be followed by a second attempt within any useful time frame. The spacecraft that had consumed years of engineering work at JPL could not be rebuilt and relaunched in time to catch the orbital window Gary Flandreau had identified. The window would close in the early 1980s as the planetary alignment that made the Grand Tour possible continued its slow celestial drift. A failure on the launch pad did not mean a delayed mission. It meant no mission, or rather, a mission deferred until 2053, when the next comparable alignment would occur, a date that made the concept of a delayed mission essentially meaningless for anyone alive on that September morning. The countdown reached 0. The Titan IIIe ignited. The spacecraft cleared the tower. The signal from the onboard transmitter arrived at the tracking stations, confirming separation and initial health. Somewhere in the crowd of engineers and scientists watching the telemetry screens, whatever had been held under tension for years released slightly. The window was being used. The spacecraft was explicitly designed for a 5-year mission, long enough to complete flybys of Jupiter and Saturn and return the primary science data from those encounters. Everything about its design reflected this expectation. The 3 radioisotope thermoelectric generators would produce approximately 470 watts of electrical power at launch, declining predictably as the plutonium-238 decayed over its 87.7-year half-life. The science instruments were designed to function within this power budget. The communication system, the data storage architecture, the attitude control thrusters, the flight data system, every subsystem was designed for 5 years of operation, after which the mission would be considered complete and the spacecraft considered done. Nobody explicitly designed anything for what actually happened, a mission that would still be actively returning science data nearly 50 years later, from a location in space that no one in 1977 had seriously expected the spacecraft to reach in operational condition. Designing for a 5-year operational lifetime imposed specific engineering constraints throughout the spacecraft's architecture that would prove unexpectedly relevant decades later. Component selection filtered out anything whose statistical failure rate made survival beyond 5 years uncertain, the principle being that over-engineering unnecessary margin cost money and mass, while under-engineering critical systems risked mission failure before the primary science was complete. The hydrazine propellant loaded for attitude control was calculated against the maneuvers required for the planetary encounters, with reserve for foreseeable contingencies but not for a mission extending 40+ years beyond the planetary phase. The onboard computers, memory capacity, and data formatting systems were built to standards appropriate for a spacecraft operating for 5 years in the space environment. The vacuum, the temperature swings between sunlight and shadow, the continuous cosmic ray bombardment on electronics that could not be shielded in any practical way. None of these systems were specifically specified for 50 years of operation. The reliability margins built into aerospace hardware as a matter of standard practice, components rated well above the minimum specifications they were required to meet, safety factors applied to calculated requirements, redundant systems for critical functions, were engineering conservatism intended to ensure that the spacecraft lasted 5 years with high confidence. That same conservatism, applied consistently throughout the design, produced a spacecraft that was still returning data from interstellar space 47 years after launch. The margin that bought 5 years of reliability bought nearly 50 instead. Voyager 1 reached Jupiter on March 5th, 1979, and what it found there permanently altered planetary science in ways that are still being felt. Scientists had expected a gas giant with interesting atmospheric features and the 4 large moons first catalogued by Galileo in 1610. What Voyager returned exceeded those expectations in every direction. The spacecraft flew close enough to Io, the innermost of the Galilean moons, to resolve its surface in unprecedented detail. The cameras showed not the ancient, heavily cratered, geologically dead world that planetary models predicted should exist at that distance from the Sun, but an active volcanic world unlike anything in human experience. Io was erupting, not occasionally, continuously and violently. 8 active volcanic eruption plumes were captured in the initial imagery. Plumes of sulfur and sulfur dioxide reaching heights of hundreds of miles, sustained by the tidal flexing of Io's interior under Jupiter's immense gravity. The surface colours were unlike anything else observed in the solar system. Oranges, yellows, reds, and whites in volcanic patterns that looked almost artificial in their vividness against the black of space. The discovery of Io's active volcanism was described by the mission scientists as one of the most astonishing findings in the history of planetary exploration. The prevailing models for how moons in the outer solar system should behave had not predicted active volcanism anywhere beyond Earth. The energy sources required for sustained volcanic activity were thought to be unavailable at those distances from the Sun. Io's heat came not from solar radiation or simple radioactive decay, but from tidal flexing, the gravitational squeezing and releasing of the moon's interior as it orbited Jupiter in resonance with the other Galilean moons. A process that generates enormous friction and heat at a scale that produces magma lakes and sustained eruption columns. A theoretical paper proposing exactly this tidal heating mechanism was published by Stanton Peele and collaborators just 3 days before the Voyager flyby, and was confirmed in the most dramatic possible way when the cameras showed the erupting plumes. The prediction and the confirmation came within days of each other, one of the most remarkable coincidences of timing in the history of planetary science. Jupiter itself exceeded every prior expectation. The Great Red Spot, observed through Earth's telescopes for centuries as a persistent storm larger than the diameter of Earth, was revealed in Voyager's imagery as a rotating atmospheric structure of mesmerizing complexity, a hurricane that had been raging continuously for at least 3 centuries and showed no signs of weakening. The faint ring system surrounding Jupiter appeared in the spacecraft's backlit photographs, rings that no Earth-based telescope had resolved, that no model of Jupiter's structure had predicted, that simply had not been part of anyone's picture of the planet. Jupiter had rings no one had known. The planet's magnetosphere was measured to be so enormous that if it could be seen from Earth with the naked eye, it would appear several times wider than the full moon in the night sky. A protective magnetic bubble dominating its cosmic neighbourhood in ways no previous measurement had fully captured. Every hour of encountered data contained something new, something that required revision of existing understanding. Among the Jupiter discoveries that would prove most consequential for the future of planetary science was something Voyager 1 glimpsed at Europa, the smooth, ice-covered second Galilean moon, whose surface looked unlike any world previously observed by a spacecraft. Europa was covered in ice, but the ice was young in geological terms. Relatively few impact craters pockmarked its surface, suggesting that something was continuously resurfacing it and erasing the cratering record that builds up on worlds where geology has gone quiet. The surface was crossed by a global network of long linear fractures and ridges, cutting through the ice in patterns suggesting the frozen shell had moved, refrozen, and moved again. The theoretical interpretation that emerged from this data, strengthened by a Voyager 2's Europa observations a few months later, pointed to a world with a subsurface ocean of liquid water maintained not by solar warmth, but by the same tidal flexing mechanism that powered Io's volcanism, operating at lower intensity. Enough internal heat to prevent a deep ocean from freezing solid beneath an insulating ice shell, at a distance from the sun where surface temperatures make liquid water thermodynamically impossible without that internal source. If liquid water existed beneath Europa's ice, that introduced a genuinely new consideration into astrobiology. Life as we understand it requires liquid water. Europa appeared to have it in darkness, under ice, far from the sun. The implications of that possibility have driven planetary science priorities ever since, and the Europa Clipper mission launched in 2024 is the direct descendant of what Voyager 1 first glimpsed. Voyager 1 used Jupiter's gravity as planned, gaining velocity and accelerating towards Saturn, arriving there on November 12, 1980. Saturn's rings, known from Earth-based telescopes as three broad bands separated by gaps, resolved into thousands of individual ringlets, each one a separate collection of ice particles and rock debris, orbiting the planet with its own dynamics and its own history. Some ringlets twisted around each other in braided patterns that orbital mechanics said should not persist, yet they persisted. The Cassini division, the most prominent gap in the ring system, long assumed to be a clean empty space swept out by orbital resonance with the moon mimas, contained ring material of its own, thin, irregular, defying the simple explanation that textbooks had offered for generations. In a single encounter, Voyager 1 demonstrated that the science of Saturn's rings, a subject that had been studied since Galileo, first observed that the planet looked somehow wrong through his early telescope in 1610, was vastly more complex and dynamically rich than anyone had appreciated. The complexity of Saturn's rings extended beyond their intricate structure to the mechanisms maintaining that structure against the natural physical processes that should destroy it. Among the clearest findings was the identification of what scientists had theorized might exist as shepherd moons, small irregular satellites whose gravitational influence confines ring particles into narrow bands by deflecting any particle that drifts outward from the ring's edge back into the ring. Voyager 1 identified two small moons flanking the narrow F-ring at Saturn's outer edge, Prometheus orbiting just inside the ring and Pandora just outside, each gravitationally herding the ring particles into the thin, bright arc that Earth-based telescopes had been observing without understanding why it persisted. The existence of these shepherd moons resolved a theoretical puzzle. Narrow rings in a planetary ring system should spread and disperse over time as orbital mechanics and interparticle collisions redistribute momentum outward. Something had to be preventing this dispersion, or the rings would not be narrow. The gravitational corralling mechanism was now directly observable, and it worked exactly as the theoretical predictions had said it should. Shepherd moon dynamics immediately became a template for understanding ring systems throughout the solar system. Jupiter's newly discovered rings, the rings of Uranus that had been inferred but not yet photographed in detail. The discovery also implied that any ring system with sharply defined narrow edges required explanation, and Shepherd satellites became the first question to ask when explaining why such edges existed. Then there was Titan. Saturn's largest moon, shrouded in orange-brown atmospheric haze, had been an object of fascination for generations. Voyager 1 approached Titan on its closest trajectory during the Saturn encounter, and the result was both exciting and maddening. The haze was real, the atmosphere was dense, but the cameras could not penetrate it to see the surface beneath. What the instruments measuring atmospheric composition and temperature returned, however, was data suggesting a world of extraordinary chemical complexity, a place where nitrogen dominated the atmosphere, where organic chemistry was producing molecules of increasing sophistication, where conditions might allow liquid hydrocarbons to pool on a surface no camera could reach. Titan kept its surface secrets, but Voyager 1's data pointed the way toward the Cassini-Huygens mission that would descend through that haze 25 years later and reveal methane rain, hydrocarbon seas, and a world more chemically complex than anything else in the solar system. The decision to study Titan closely carried an irreversible consequence for Voyager 1's trajectory. To approach closely enough to gather useful data required directing the spacecraft into a path angled steeply out of the plane of the solar system, permanently closing off any further planetary encounters. Voyager 2, following a different path from a different launch trajectory, would go on to become the only spacecraft ever to visit all 4 outer planets in a single mission, reaching Uranus in 1986 and Neptune in 1989. Voyager 1, its planetary mission complete at Saturn, was done with planets. What lay ahead was the vast, dark, unmeasured outer heliosphere, a region extending outward through distances that dwarfed everything the spacecraft had already crossed, and beyond that, something that had never been directly measured at all. The scientists managing the mission understood that Voyager 1 was not heading into retirement. It was heading into unexplored territory that no instrument had ever entered, carrying systems designed for a 5-year planetary mission that would now be asked to do something no one had originally planned for them to do. For the scientists and engineers whose careers had been built around the planetary encounter phase of the mission, Saturn represented a peculiar kind of ending. The Jupiter encounter had exceeded every expectation. Saturn had produced equally stunning science, rings revealed as thousands of ringlets, Shepherd moons discovered, Titan's atmospheric complexity confirmed, more moons found than anyone expected. But after Saturn, after the encounter data had been transmitted, archived, and handed to the researchers who would analyse it for years, Voyager 1's trajectory diverged permanently from any further planetary encounter. The path out of the ecliptic plane, chosen for the Titan science it enabled, pointed the spacecraft into the unmapped outer heliosphere with nothing resembling a planetary system ahead of it for the foreseeable future. The engineering and navigation teams who had spent years planning the precision geometry of the Jupiter and Saturn flybys faced the reality that their spacecraft was done with planets. Some transitioned to Voyager 2, which still had its Uranus and Neptune encounters ahead in 1986 and 1989, and would provide the focused planetary encounter work they were trained for. Others stayed with Voyager, one for an extended heliospheric mission whose scientific importance was genuine, but whose timescale and character were entirely different from anything the planetary encounter phase had demanded. The spacecraft that had been the focal point of enormous, concentrated attention was becoming a slowly receding data source, its position measured in billions of miles rather than hours until encounter. What Voyager 1 would be crossing during those decades of outward travel was the heliosphere, the enormous bubble carved out of the interstellar medium by the sun's solar wind. The solar wind is a continuous stream of charged particles expelled from the sun's corona at speeds of hundreds of miles per second, flowing outward in all directions, filling the space around the sun for billions of miles in every direction. It is the sun's breath, constant and relentless, pushing against the surrounding interstellar medium, the thin, gas, dust, and magnetic field filling the space between stellar systems. Where the solar wind pushes hard enough, it holds the interstellar medium at bay, creating a region of space where conditions are shaped by the sun rather than by the galaxy. The heliosphere is that region. Everything inside it lives, in a meaningful sense, within the sun's domain. Everything outside it exists in the interstellar medium, the space between the stars. The heliosphere that Voyager 1 would be crossing exists because the sun does not merely warm its surrounding space by radiation. The sun also sustains a continuous outflow of charged particles from its outer atmosphere, the corona, driven by the same thermodynamic processes that heat the corona to millions of degrees, while the sun's visible surface sits at only a few thousand degrees. This outflow, called the solar wind, was theoretically predicted by Eugene Parker in 1958, when most physicists believed interplanetary space was essentially empty. Parker's mathematics showed that the corona's extreme temperature created a pressure gradient that would accelerate gas outward through the solar system indefinitely. Mariner 2 confirmed the solar wind's existence in 1962, measuring the streaming plasma directly during its transit toward Venus. The solar wind flows from the corona at speeds ranging from roughly 300 to 800 kilometers per second, depending on solar activity, carrying the sun's own magnetic field embedded within it like iron filings, suspended in a river's current. This magnetized plasma fills the space between the planets, sculpts the magnetospheres of every planet it encounters, strips away the atmospheres of unprotected worlds over geological time, and inflates the heliosphere outward against the pressure of the surrounding interstellar medium in every direction from the sun. The heliosphere is not a fixed structure. It breathes with the sun's activity cycle, expanding when the solar wind strengthens and contracting when it weakens, a dynamic boundary maintained by the balance of two continuously varying pressures. The boundary structure of the heliosphere had been studied theoretically for decades before Voyager 1 was in a position to test any of those theories. Physicists working from the mathematics of fluid dynamics had predicted a specific architecture. The solar wind, flowing outward at supersonic speeds, would eventually encounter the inward pressure of the interstellar medium and be forced to slow dramatically, forming a shock wave called the termination shock. Beyond the termination shock, the solar wind would still exist but would be slowed, heated, and compressed into a turbulent region called the Helios Heath. And beyond the Helios Heath lay the heliopause, the true outer boundary, the place where solar material gave way entirely to interstellar medium, and the sun's direct influence effectively ended. 3 boundaries, 3 distinct regions, each with its own predicted properties, each waiting for the first instrument to reach them. Voyager 1 was heading toward all 3. Voyager 1 was not the first spacecraft to head outward from the inner solar system into the unmapped spaces beyond Jupiter. Pioneer 10 and Pioneer 11, launched in E72 and in 73 respectively, had already blazed the route, demonstrating that the asteroid belt could be traversed without catastrophic particle impacts, and returning the first close-up images of Jupiter's cloud structure and magnetosphere. Pioneer 11 was redirected after Jupiter to provide a Saturn flyby preview in 1979, arriving months before Voyager 1, and confirming the general structure of the ring system and magnetosphere. Both Pioneer spacecraft had simpler instrument packages than the Voyagers, and both were travelling outward through the outer heliosphere as the 1970s ended and the 1980s began, their power systems declining on a faster schedule than the Voyager RTGS Pioneer 10 was transmitting from beyond the orbit of Pluto when its signal became too weak to detect reliably in the early 2000s. Pioneer 11's last contact came in 1995. Neither spacecraft carried instruments sensitive enough to clearly characterize the termination shock crossing, and the ambiguity of their data from the outer heliosphere left the location of that boundary uncertain for years. Pioneer had opened the road and demonstrated it was survivable. but the instruments and power systems required to actually measure the heliosphere's outer boundaries with scientific precision had to wait for Voyager 1 to arrive at those distances with its more capable payload still functioning. The challenge of predicting exactly where these boundaries would be located was substantial. The termination shock's distance from the Sun depended on the balance between the solar wind's outward pressure and the interstellar medium's inward pressure, both of which varied with solar activity, with direction, and with the properties of the local interstellar environment around our specific part of the galaxy. Early models suggested the termination shock might sit at roughly 50 to 100 astronomical units from the Sun. The uncertainty range was large because neither the outward-pushing solar wind pressure nor the inward-pushing interstellar medium pressure could be measured at the boundary. They could only be extrapolated from measurements taken at known locations. The models gave ranges rather than points, confidence intervals rather than precise predictions. What they all agreed on was that Voyager 1 would eventually reach these boundaries if it continued operating, and that the data it would return when it did would be unlike anything science had access to before. The first of the predicted boundaries fell in December 2004. Voyager 1 was approximately 94 astronomical units from the Sun, nearly 8.7 billion miles out, when its instruments registered an abrupt deceleration in the solar wind velocity, a spike in particle density, and a jump in magnetic field strength. The solar wind, which had been flowing outward at supersonic speeds since the spacecraft's launch 27 years earlier, had suddenly slowed where the pressure of the interstellar medium finally balanced its outward momentum. The termination shock was not a theoretical construct, it was a real place with measurable properties at a specific distance from the Sun. Edward Stone, the mission's project scientist since 1972, and now more than 3 decades into his oversight of the Voyager science program, described the crossing as a moment the team had been working toward for years. The transformation of a physical prediction into an observed reality. The details of what the instruments recorded as Voyager 1 passed through the termination shock were scientifically rich in ways that took researchers years to fully extract. The particle instruments showed that solar wind protons were being heated at the shock to temperatures substantially higher than simple compression models predicted, implying more complex energy transfer processes operating at the boundary than the textbook shock physics assumed. The cosmic ray detector revealed that the termination shock was functioning as a particle accelerator in the way that shock fronts elsewhere in the universe are known to function, reflecting some fraction of particles back into the upstream solar wind at higher energies through the mechanism called diffusive shock acceleration, the same process thought to operate at supernova remnant shocks and galactic cosmic ray sources throughout the universe. The specific energy spectrum and efficiency of this acceleration provided new observational constraints for models of how the heliosphere processes the particle populations flowing through it. The magnetic field measurements at the crossing showed the shock to be not a simple smooth surface, but a dynamic corrugated boundary with structure across multiple scales, fluctuating in time, varying in strength and compression ratio, behaving in ways the smoothed average models had not fully captured. Each of these findings replaced a theoretical assumption with an observed reality, producing the specific numbers that constrained the next generation of models and pointed toward new questions that the heliosheath crossing would address. What the instruments recorded at the termination shock crossing was revealing but not perfectly consistent with the predictions. The shock was sharper than expected in some parameters and more diffuse in others. The magnetic field behavior at the boundary showed characteristics that existing models had not captured. These discrepancies were not failures, they were the beginning of a more sophisticated understanding. The data from the termination shock provided specific observational constraints that theorists could work with. Specific numbers to explain, specific features to account for, specific places where existing models showed their limitations. Science advances through exactly this process, and Voyager 1 was providing the raw material for it in a location that no other instrument could reach. Voyager 1 was now in the heliopause heath, the turbulent, compressed region of slowed solar wind lying between the termination shock and the heliopause. It would spend approximately 8 years crossing this region, and the data it returned during that crossing continued to challenge and revise the theoretical picture of the outer heliosphere. The heliosheath was not the smooth, predictable transition zone that some models had assumed. The instruments detected magnetic field reversals, regions where the field direction flipped unexpectedly. They measured density variations that correlated with large-scale structures, and then they found something that had not been predicted at all: magnetic bubbles. These were large-scale regions of twisted magnetic field structures tens of millions of miles across, forming at the outer edge of the heliosphere in a way that created what the data described as a complicated, foam-like architecture rather than a simple, smooth layered boundary. The theoretical picture of an organized outer boundary was replaced by something more complex and more dynamically interesting. The 8 years Voyager 1 spent crossing the heliopause heath, the turbulent, compressed region of slowed solar wind material lying between the termination shock and the heliopause, provided a sustained sequential record of a region that theoretical models had described as a relatively ordered transition zone. The actual data told a more complicated story. The magnetic field in the heliosheath showed reversals, regions where the field direction flipped to the opposite orientation, suggesting the outer solar magnetic field was organized into distinct polarity sectors separated by current sheets, rather than the relatively smooth spiral that models had assumed. Particle populations evolved with distance from the termination shock in ways reflecting complex dynamics in the compressed heliosheath plasma, and then the instruments found something the models had not clearly anticipated. The outer heliosphere's magnetic field was folding into large-scale closed loops, magnetic bubbles tens of millions of miles across, forming where the outward-pushing solar magnetic field became kinked and folded by turbulent heliopause heath conditions into structures that resembled foam more than the simple layered boundary that theoretical pictures had implied. The detection of these bubbles changed the conceptual model of what the outer heliosphere looks like. Not a smooth laminar flow of compressed solar wind gradually transitioning to interstellar medium, but a dynamically complex, structured, bubbly environment where magneto-hydrodynamic processes operate on scales from the very small to the astronomically vast. Then, in the summer of 2012, the readings began to change in a way that was qualitatively different from anything that had come before. Throughout the heliosheath crossing, the instruments had been tracking 2 populations of particles as diagnostic markers of the spacecraft's position relative to the heliopause. Low-energy ions and electrons from the Sun, solar particles streaming outward through the heliosphere, and galactic cosmic rays, high-energy particles from supernovae and other violent galactic events, partially screened out by the heliosphere's magnetic field but penetrating in reduced numbers. The ratio of these 2 populations was the primary gauge for tracking how close the spacecraft was getting to the outer boundary. Scientists had been watching this ratio carefully for years, looking for the shift that would signal the crossing. In late July 2012, the ratio shifted dramatically. The count of low-energy solar particles, which had been a constant presence throughout the entire mission, dropped sharply within days. The galactic cosmic ray count spiked to the highest level the instruments had ever recorded. Something significant had happened. The team analysed the data carefully. This shift was more sudden and more complete than the gradual transition the models had predicted. Then the counts partially recovered before shifting again, more definitively. And then, on August 25, 2012, the measurements changed in a way that did not reverse. The low-energy solar particles essentially vanished from the instrument readings. The galactic cosmic ray count reached a new plateau and stayed there. the plasma environment changed abruptly and did not change back. The team was cautious about what this meant. Cautious, but aware that something very significant had happened. The scientists watching the data arrive from Voyager 1 in real time at JPL during the late summer of 2012 understood they might be witnessing something historic, but had also trained themselves over decades to withhold conclusion until confirmation was unambiguous. The abrupt drop in low-energy solar particles and simultaneous spike in galactic cosmic rays in late July 2012 was striking in the real-time plots. Not subtle statistical trends, but sharp transitions visible against the backdrop of years of relatively steady readings. But heliospheric scientists had encountered false signals before. In 2010 and again in 2011, transient magnetic field changes had produced particle fluctuations that some researchers had interpreted prematurely as signs of an approaching heliopause, only for the readings to recover toward their previous values days later. The team had explicitly committed to a standard of evidence that would not be satisfied by particle count changes alone, no matter how dramatic. The plasma density measurement, which required a triggering solar event to produce detectable oscillations, was the specific confirmation criterion they were waiting for. So in the late summer of 2012, they watched the particle counts stay changed through August and into early September, day after day without the recovery that had previously unmasked the false alarms, and continued planning the specific observation that would produce the unambiguous confirmation, knowing it could only come on the solar system's own timetable. The confirmation of what had happened required a specific measurement that the plasma wave science instrument could only take given the right triggering conditions. This instrument could measure the density of the surrounding plasma by detecting how it oscillated in response to pressure waves from the Sun, but making that measurement required a pressure wave from a solar energetic particle event to reach Voyager 1's position and excite the plasma into oscillations at a frequency tied directly to its density. The team had to wait for a wave produced by a solar event in the spring of 2013 to propagate outward across billions of miles to the spacecraft's position. When that wave arrived and the plasma wave instrument recorded the resulting oscillations, the data was unambiguous. The plasma density surrounding the spacecraft had increased by approximately a factor of 40 relative to what had been measured in the heliosphere. This was precisely the signature of the interstellar medium. Voyager 1 was in interstellar space. On September 12, 2013, NASA held a press conference. Edward Stone stood before cameras and stated clearly what the accumulated data showed. Voyager 1 was in interstellar space, the first human-made object in history to enter the space between the stars. The sentence is brief. The weight behind it is almost impossible to fully absorb even now, more than a decade after the announcement. Every prior achievement of human space exploration, every landing, every flyby, every orbit, every probe plunged into a planetary atmosphere had taken place within the Sun's domain, within the protective heliosphere our star maintains around itself. Voyager 1 had left that domain. It was in the space that separates stellar systems. It was in the same kind of emptiness that the light from the stars crosses on its journey to our eyes. No instrument built by human hands had ever been there before. The scientific significance of the heliopause crossing announcement extended well beyond its intrinsic drama. For heliospheric physicists, September 12, 2013 represented the first observational test of theoretical models built over several decades without direct measurement from the location being modelled. Every prediction about the heliopause, its distance from the Sun, the plasma density change at the crossing, the magnetic field behaviour, the particle population transitions, could now be evaluated against actual data from the actual boundary rather than being extrapolated from theory. Some predictions survived this test well. The plasma density increase at the crossing was within the range the best models had allowed, though at the high end. The particle population changes were abrupt in a way broadly consistent with theoretical expectations for a sharp boundary rather than a diffuse transition. Other predictions fared less well. The magnetic field direction's persistence across the boundary contradicted the clear rotation that the leading theoretical models had predicted, and this discrepancy became the focus of intense scientific debate that continues today. The overall lesson the field absorbed was not that the models were wrong in any simple sense, but that they had been built with inadequate observational constraints, and that the specific places where they succeeded and failed now provided a roadmap for which physical processes needed better treatment in the next generation of models. This is what it looks like when science is working. A confrontation between theory and direct observation produces not just new facts, but sharper questions. The confirmation of Voyager 1's interstellar location reoriented how the scientists working on the mission thought about what they were doing. Researchers who had spent careers as heliospheric physicists studying the solar system's outer domain found themselves reclassified into practitioners of something genuinely new: the direct, observational study of the local interstellar medium. The questions driving the mission's science shifted qualitatively. Before the crossing, the program's central questions were about the solar system's own structures. Where exactly was the termination shock? What was the heliosheath's density and magnetic character? Where was the heliopause? After the crossing, the questions became about the universe beyond. What is the plasma density in the local interstellar medium, and how does it vary with distance from the heliopause? What is the temperature of this gas? What does the galactic magnetic field look like at this specific location in the galaxy? How does solar activity transmit its influence across the heliopause boundary into the interstellar medium? These are different questions at a different level of the physical hierarchy. The researchers who had spent their careers studying the edge of the ocean now found themselves in the ocean itself, with instruments never designed for the ocean, in water whose properties they had only ever modelled from the shore. The shift was exhilarating and humbling in equal measure, and it produced a decade of papers revealing just how much the models built from the shore had gotten wrong about conditions in the water. The question that immediately arose, and has not stopped being asked since, was what Voyager 1 actually found in that space. The answer has been consistently and genuinely surprising. Not surprising in the minor way that small discrepancies from prediction occasionally surprise researchers. Surprising in the deeper sense, where the data contradicts the theory so significantly that the theory must be reconsidered. Begin with the plasma density. The factor of 40 increase that confirmed the crossing was itself scientifically informative. The theoretical models of the interstellar medium built over decades of heliospheric physics research had made specific predictions about what the plasma density just outside the heliopause would be. The actual measurements came in within the predicted range, but at specific values that allowed theorists to significantly refine their picture of the local interstellar environment. This matters because the local interstellar medium is not a uniform environment. Our solar system sits inside what astronomers call the local bubble, a vast cavity, roughly 1,000 light-years across in some directions, hollowed out by supernova explosions millions of years ago and filled with hot and relatively thin plasma. Our sun has been drifting through this bubble for approximately 5 million years, and the properties of the plasma in this particular region of the galaxy have direct consequences for the heliosphere's size and shape. Voyager 1's measurements were, for the first time, providing actual numbers from the actual location, rather than theoretical extrapolations based on observations made from far away. Then there was the magnetic field, and what it did not do. Before the crossing, the expectation in heliospheric physics was clear. The magnetic field direction would change significantly at the heliopause. Inside the heliosphere, the sun's magnetic field spirals outward in what physicists call the Parker spiral, a pattern created by the combination of the sun's rotation and the radial outflow of the solar wind, oriented predominantly in the plane of the solar system. In the interstellar medium, the field was expected to reflect the local galactic magnetic field, inferred from various astronomical observations to be oriented in a meaningfully different direction. The theoretical prediction was a clear rotation in the measured field direction at the heliopause boundary. What the magnetometer recorded was unexpected. At the boundary, the field direction did not rotate significantly. Strength changed, other properties changed, but the orientation remained roughly similar across the transition. This was not what the models had predicted, and it generated scientific debate that continues today. Whether the local interstellar magnetic field happens to be nearly aligned with the heliospheric field in the region Voyager 1 crossed, or whether the boundary is more complex than the models assumed, is still being argued in the literature. The lack of significant magnetic field rotation at the heliopause generated a scientific debate that the subsequent years have complicated but not resolved. Several distinct theoretical interpretations emerged in the literature following the announcement. The first holds that the local interstellar magnetic field genuinely happens to be nearly aligned with the heliospheric field in the specific region Voyager 1 crossed. A coincidence of local geometry reflecting the orientation of the galactic magnetic field in our immediate stellar neighbourhoods, which could in principle be verified or refuted by a spacecraft crossing the heliopause in a sufficiently different direction. The second interpretation argues that the heliopause is a more complex transition zone than the simple surface the models assumed, with the two magnetic environments gradually merging across a thick boundary layer rather than meeting at a sharp interface, and that the conditions of the specific crossing Voyager 1 made happened to sample this gradual transition in a way that obscured the underlying rotation. A third class of models incorporates the possibility that the heliosphere is not spherically symmetric, that the galactic magnetic field pressing on the heliopause from outside distorts its shape in a way that makes the field nearly parallel to the boundary surface at the location of the crossing. Voyager 2's 2018 heliopause crossing at a different angle provided new data that has added constraints to this debate without fully resolving it. The field behaviour at Voyager 2's crossing showed similarities to but also differences from what Voyager 1 had measured, adding complexity to a picture that is still being assembled. The cosmic ray environment beyond the heliopause has provided some of the most practically significant findings. Inside the heliosphere, the Sun's magnetic field partially shields the inner solar system from galactic cosmic rays, high-energy particles accelerated by supernovae and other violent galactic events, which pose real radiation hazards to biological tissue and electronics. Once Voyager 1 crossed the heliopause, the cosmic ray flux increased by a factor of roughly 2 to 3 compared to what was measured just inside the boundary. This is critical data for future exploration. Any crewed mission that might someday venture beyond the heliosphere would face a substantially more hostile radiation environment than anything encountered within our stellar neighbourhood, and the specific energy spectrum and particle composition of the interstellar cosmic ray flux, which only Voyager 1 currently measures, is essential input for designing the systems that would have to protect crew and instruments in that environment. The cosmic ray measurements have also revealed something more subtle and scientifically significant. The local interstellar medium appears to modulate the cosmic ray flux even outside the heliosphere. The truly unmodulated galactic cosmic ray background, the raw flux as it exists throughout the broader interstellar medium of the galaxy, may be somewhat higher than what Voyager 1 is measuring. The spacecraft is travelling through the local bubble, a region with its own particular plasma properties that appear to affect how cosmic rays propagate through it. Separating the effects of heliospheric shielding from the effects of the local bubble environment and determining what the truly unmodulated galactic cosmic ray flux looks like is one of the ongoing scientific challenges that Voyager 1's continued measurements are positioned to address as the spacecraft moves farther from the heliopause into progressively less disturbed interstellar plasma. Understanding the local bubble is not merely a problem in galactic cartography. Our solar system has been moving through this region, a vast, roughly ellipsoidal cavity roughly 1,000 light-years across in some directions, evacuated by the explosions of multiple supernovae millions of years ago and refilled with hot, tenuous plasma for approximately 5 million years. The conditions within the local bubble differ significantly from the galactic average. Lower density, higher temperature, weaker magnetic field than what the broader interstellar medium of the Milky Way would provide on average. These conditions directly shape the heliosphere. A denser surrounding interstellar medium would compress the heliosphere inward, bringing the heliopause closer to the inner solar system and reducing the heliospheric shielding of the Earth from galactic cosmic rays. Our current position within the relatively thin local bubble plasma allows the heliosphere to be correspondingly large. Whether this has measurable consequences for life on Earth, through the cosmic ray flux reaching the planet's surface, through effects on the upper atmosphere, through mechanisms that remain actively debated, is a genuine scientific question. The hypothesis that galactic environmental changes have influenced terrestrial biology through their effects on the heliosphere is investigated seriously at the margins of heliospheric science, and the specific plasma properties Voyager 1 measures in the near interstellar medium provide the only direct boundary conditions these investigations have ever had access to. The Plasma Wave Science Instrument has been one of the most productive sources of ongoing discovery since the crossing. It provided the definitive plasma density measurement that confirmed entry into interstellar space, and it has continued operating, detecting oscillations in the surrounding plasma that reveal the medium's response to disturbances propagating outward from the Sun. The key finding is that the interstellar plasma surrounding Voyager 1 is not quiet. It vibrates, it resonates, it responds to events that originate at the Sun, propagate through the heliosphere, cross the heliopause, and continue into the near interstellar medium as pressure waves that can still measurably compress and excite the surrounding plasma. Large-scale disturbances produced by coronal mass ejections and solar energetic particle events travel outward through the solar wind and, even after crossing the boundary, continue to influence the plasma at Voyager 1's position. The team has identified at least 3 distinct plasma oscillation episodes in interstellar space since the 2012 crossing, each one correlated with a solar energetic event that launched the triggering wave months or years before the oscillation arrived at the spacecraft's position. The plasma oscillation episodes detected by the Plasma Wave Science Instrument in interstellar space each have traceable origins in specific solar events whose timelines can be reconstructed across the years separating their causes from their effects at Voyager 1's position. The first episode, recorded in October and November 2012, was triggered by a pressure wave produced by an intense solar energetic particle event in the spring of 2012, a wave that propagated outward through the solar wind, crossed the heliopause, and compressed the interstellar plasma at Voyager 1's location into detectable oscillations roughly 6 to 8 months after the originating solar event. The second episode, recorded in April and May 2013, traced back to another major solar energetic particle event several months prior. The third, in March 2014, had a comparable origin. Each episode provides a measurement of the local electron density at the spacecraft's then current position, because the oscillation frequency depends directly on that density in a way the plasma wave instrument can precisely measure. The extraordinary aspect of these observations is the physical chain they represent. A violent event on the Sun's surface launches a pressure disturbance. That disturbance propagates through the heliosphere at solar wind speeds, crosses the heliopause into the interstellar medium, and arrives at Voyager 1's position months or years later as a compressional wave that the spacecraft detects and that provides a density measurement for a specific point in interstellar space. Sun to spacecraft to Earth, a chain of causation spanning billions of miles and years of elapsed time. Each plasma oscillation event provides a fresh measurement of the local plasma density at Voyager 1's current location. Because the spacecraft is continuously moving, each measurement represents a slightly different point in space. Over the years since the crossing, these episodic density measurements have been building a picture of how the plasma density changes with increasing distance from the heliopause, a spatial profile that could not be constructed through any other method. The data shows that density is not constant. It varies with distance from the boundary as the spacecraft moves into progressively less disturbed interstellar medium, and it varies with time as different pressure waves from different solar events arrive and pass. The interstellar medium directly outside the solar system is dynamic, still shaped by solar activity transmitted through the heliopause, still exhibiting structure that reflects processes operating on a range of scales. This finding carries implications that extend well beyond the specific measurements Voyager 1 is collecting. Every star in the galaxy pushes its own heliosphere into the surrounding interstellar medium. Every stellar wind creates its own termination shock, its own helios heath, its own heliopause. And every stellar wind maintains a dynamic interaction with the surrounding medium that does not simply cease at the outer boundary. Energy continues to transfer across it, disturbances continue to propagate through it, and the medium on the other side continues to respond. Voyager 1 is measuring this interaction from the outside looking in, at the specific location where our Sun's heliosphere meets the local interstellar medium. The physics it is revealing applies, in principle, to every stellar system in the galaxy. We are building a template for understanding a universal process using the only direct measurement that exists. The implications of what Voyager 1 is measuring extend far beyond the specific physics of our solar system to every stellar system in the galaxy. Every star that sustains a stellar wind, which includes the overwhelming majority of stars, creates its own version of the heliospheric structure Voyager 1 has characterized. A termination shock where the stellar wind slows, an analogue to the Helios heath where the compressed stellar wind material creates a turbulent transition zone, and a boundary analogous to the heliopause where stellar material gives way to the surrounding interstellar medium. The physics governing all of these structures is identical in its mathematical form. Plasma dynamics, magnetic field evolution, particle acceleration at shocks, the mediation of energetic particles by the stellar magnetic environment. What differs between stellar systems is the parameters, the strength and variability of the stellar wind, the density and magnetic properties of the local interstellar medium into which the heliosphere pushes the size of the resulting structure. What Voyager 1's measurements provide is observational calibration of these universal processes at the one specific example where direct measurement is possible. This calibration matters for exoplanetary science in a specific way. The size of a stellar heliosphere determines how much galactic cosmic ray shielding planets within it receive, which in turn affects atmospheric chemistry and the radiation environment at a planet's surface. Understanding that shielding through direct measurement rather than inference gives the study of exoplanetary habitability a concrete reference point it previously lacked. One of the most intriguing ongoing findings involves what is absent from the interstellar measurements. Inside the heliosphere, the instruments recorded a broad, roughly continuous distribution of particle energies from the lowest energy solar wind ions through intermediate ranges up to the highest energy galactic cosmic rays. In interstellar space, the low-energy solar particles vanished as expected when the spacecraft crossed the heliopause. But at intermediate energies, a range between the disappeared solar particles and the clearly galactic high-energy cosmic rays, the measured population is lower than models of the interstellar medium predicted. Several competing explanations have been proposed that it reflects the specific properties of the local bubble, whose particular plasma supports a different particle population than the broader interstellar medium farther out. That it reflects the differential filtering effect of the heliosphere across different energy ranges leaving an imprint of the solar system's shielding capacity visible in the post-boundary measurements, or that it reflects some process in the near-interstellar medium itself that is not yet captured in existing models. Resolving this question requires continued measurements as Voyager 1 moves farther from the heliopause, which is exactly what it is doing. Voyager 1 is moving. This point deserves emphasis because it is easy to picture the spacecraft as having reached a boundary and stopped at it, like a probe planted at a shoreline. It has not stopped. It is travelling at approximately 17.1 kilometers per second, roughly 38,000 miles per hour, in a direction angled roughly 35 degrees above the plane of the solar system, heading toward the constellation Ophiuchus. Each year it covers approximately 3.6 additional astronomical units of new territory. In the decade since the 2012 heliopause crossing, it has moved from 21 astronomical units to more than 165 astronomical units from the Sun, 44 additional astronomical units of interstellar space that no instrument had sampled before Voyager 1 reached each successive position. Every new data point is a measurement from a location that has never been measured before, and the comparison of measurements taken at different distances is building a spatial profile of the near-interstellar medium that has no precedent and no substitute. The spatial profile being constructed by Voyager 1's continuous movement through interstellar space is a scientific dataset with a characteristic that makes it more valuable with each passing year, rather than less. No other observational method, no Earth-based telescope, no observatory at any location within the solar system, no inference from remote observations of other stellar systems can produce a sequential set of direct measurements at progressively increasing distances from our heliopause into the near-interstellar medium. The reading at 122 astronomical units establishes the plasma density, magnetic field strength and direction, and cosmic ray spectrum at that specific point. The reading at 135 astronomical units does the same for that location. At 50 and 165 and beyond, each new measurement occupies a specific position in a spatial profile that has never existed before and cannot be created by any other means. As this profile accumulates length with each additional year of mission operation, it progressively constrains the theoretical models that attempt to describe the structure of the near-interstellar medium. Models consistent with measurements at 122 astronomical units, but inconsistent with what is measured at 45 can be excluded. Models that account for both must explain the difference. Each additional measurement point tightens the constraint further. In this respect, the last years of Voyager 1's active data collection may be producing science of greater power per measurement than any previous phase of the mission, an unusual situation for an aging spacecraft whose technical capabilities can only decrease with time. The changes being recorded as Voyager 1 moves outward are real but subtle, exactly what would be expected from gradual movement through a medium that is not perfectly uniform. The plasma density appears to increase slightly with distance from the heliopause, consistent with moving from a region still somewhat influenced by the Sun's long-term passage through the interstellar medium toward a region of more undisturbed interstellar plasma further from the heliospheric boundary. The cosmic ray flux shows gradual changes in its detailed composition, with some energy ranges changing more than others, providing clues about how the heliosphere modulates different particle populations to different degrees. The magnetic field shows slow variations that may reflect genuine spatial structure in the local interstellar medium. Every measurement adds something to human knowledge about the universe outside the solar system that cannot be added any other way. What is perhaps most remarkable about the ongoing science from Voyager 1 is not any individual discovery, but the simple, persistent fact that the science continues at all. Every power system model produced in 1977 predicted the instruments would long since have gone dark. The original design lifetime was 5 years. The spacecraft is approaching 50 years of continuous operation, a factor of nearly 10 beyond its designed lifetime. No one who built Voyager 1 designed any of its systems with the expectation of 50-year operation in mind. No one wrote procedures for maintaining a spacecraft this old. No one planned for the generational transfer of knowledge that has become necessary to keep the mission running. The spacecraft has outlasted its creator's expectations through a combination of engineering conservatism, meticulous power management across 5 decades, and an institutional commitment at NASA that has kept the mission staffed and funded through budget cycles, personnel changes, and the deaths of many of the scientists and engineers who conceived and built it. The scientific achievement of the extended Voyager mission is inseparable from a quieter and less publicly celebrated accomplishment. The organisational and managerial work required to sustain a deep space mission across nearly 5 decades of changing institutional priorities, funding environments, and personnel. Keeping any scientific program alive through multiple presidential administrations is a non-trivial political and bureaucratic challenge. Keeping one alive through the specific cycles of attention and neglect that characterize NASA's budget environment, where crude spaceflight priorities periodically dominate at the expense of planetary science, where new flagship missions generate excitement that can make older missions seem less urgent, where the age of a program can be framed as a reason to let it end rather than to extend it, required sustained and successful argument for the mission's continuing value in every budget cycle since the late 1970s. JPL has made that argument successfully, year after year, by demonstrating that the data returning from Voyager 1 is scientifically unique in a way that cannot be substituted by any other available source. The argument was always technically true, but making it persuasively within the institutional dynamics of a large government agency, while also managing the actual spacecraft and extracting actual science from it, required a kind of sustained organisational commitment that has no glamorous name and receives no dramatic public recognition. Without it, the interstellar science would not exist. The power situation is the most critical ongoing constraint. Voyager 1's electricity comes from 3 radioisotope thermoelectric generators, sealed units containing plutonium-238, whose radioactive decay produces heat that thermocouple arrays convert into electricity. At launch, the RTGs produced approximately 470 watts. Plutonium-238 decays with a half-life of 87.7 years, producing a predictable power decline of roughly 4 watts per year. As of the mid-2020s, the power output had fallen to approximately 270 watts, a reduction of 200 watts from the launch value. This forced a decades-long exercise in triage, determining which systems to keep running and which to shut down, in an order that preserves the most scientifically valuable observations for as long as possible, while permanently sacrificing everything that cannot be afforded anymore. The history of these shutdowns reflects the history of a mission in continuous triage. Voyager 1 originally carried 11 science instruments. The imaging cameras and their associated scan platform were shut down in 1990. After Carl Sagan's request for the pale blue dot family portrait was fulfilled, the cameras had done their work at Jupiter and Saturn, there was nothing visible to photograph in the outer heliosphere, and their power could be better used by instruments still actively measuring the environment. Heaters for instruments whose primary science had been completed were switched off one by one, accepting the risk of cold damage in exchange for precious watts. Each shutdown was a deliberate sacrifice, a permanent closing of an observational window, made with full awareness that the window would not reopen, and that the instruments being closed had already far exceeded anyone's expectations for what they would accomplish. The decisions about which instruments to shut down as power declined were not made through a simple formula, but through a process that required sustained scientific judgment under irreversible conditions. Each shutdown was preceded by formal review, an assessment of what the instrument to be turned off was still measuring, what scientific questions it could still address, what its continued operation would contribute to the mission versus what turning it off would cost the program permanently. These reviews were sometimes contentious. Principal investigators who had built careers around specific experiments held views about the continued value of their instruments that did not always align with the priority rankings the project scientist's office produced. The physics, however, could not be negotiated with. The power was declining at roughly 4 watts per year, regardless of anyone's preferences, and the choice was not between keeping all instruments and sacrificing some, but between making reasoned, explicit priority decisions on the team's own schedule or waiting for the power to drop below the threshold for running all remaining instruments and having the decision made by default at a moment not of the team's choosing. The team chose to exercise control over its own science priorities, making deliberate sacrifices on a timeline to preserve the instruments judged most scientifically critical for as long as the remaining power budget allowed. This is what responsible stewardship of a diminishing resource looks like: accepting the losses you cannot avoid, choosing which ones to accept first, and remaining intentional about the choice until the final watt is gone. As of the mid-2020s, Voyager 1 operates 4 active science instruments. The cosmic ray subsystem measures the energy and composition of cosmic rays streaming in from interstellar space, providing the detailed spectral data needed to characterize the radiation environment outside the heliosphere. The low-energy charged particle instrument tracks particles in the lower energy range, covering the remaining low-energy particle population in the interstellar medium. The magnetometer measures the local magnetic field with extraordinary precision, tracking how it changes as the spacecraft moves through the interstellar medium. The plasma wave science instrument listens to oscillations in the surrounding plasma, providing the density measurements that continue refining understanding of the local interstellar environment. These 4 instruments, kept alive through careful power management across nearly 5 decades of continuous operation, constitute the most remote active scientific observatory in human history. Each of these instruments was designed in the early 1970s using electronics that are, by any modern standard, extraordinarily primitive. The onboard computers operate on logic that would have been recognizable to Apollo-era engineers, processors whose speed is measured in thousands of operations per second rather than the billions of modern chips. The memory available for data storage would fit comfortably on a single short audio file by modern standards. The software running the spacecraft systems was written by hand in programming languages that are now historical artifacts, by engineers who could not have imagined the world in which their code would still be running half a century later. And yet these systems continue to function in the most extreme environment any human-made object has ever occupied. Temperatures near the cosmic background radiation's baseline of a few degrees above absolute zero, continuous bombardment by cosmic rays, isolated from any support or maintenance by 15 billion miles, and a 23-hour signal delay in each direction. The people who built Voyager 1 are mostly gone now. The engineers who assembled it in the clean rooms at JPL in the mid-1970s have retired, aged, and many have died. The institutional knowledge of the spacecraft's specific behaviour, the particular way its aging systems respond to commands, the accumulated wisdom about its quirks and failure modes built up over nearly 50 years of continuous operation, the context behind procedures that exist for reasons no longer immediately obvious from any existing document, has had to be transferred across multiple generations of mission personnel, some of whom were not yet born when the spacecraft launched. This transfer of knowledge is not a simple documentation problem. It is a genuinely difficult challenge of communicating not just what the spacecraft does, but why certain procedures exist, what failure modes they prevent, and how the system behaves in edge cases no manual explicitly anticipated. The knowledge lives most reliably in experienced human memory, and must be intentionally passed before those who hold it can no longer pass it. Edward de Stone, who served as the missions project scientist from 1972 until 2010, an unbroken tenure of nearly 5 decades, is perhaps the most important example of this kind of institutional continuity. Stone was present for the Jupiter flyby, the Saturn flyby, the termination shock crossing, the heliopause crossing, and the first years of interstellar science. He was the public face of the mission's discoveries for most of its operational lifetime, and he accumulated a depth of contextual understanding about the mission's history and the spacecraft's behaviour that no document could fully capture. When he retired from the project scientist role in 2019, the mission lost something irreplaceable. Not his expertise, which could be partially documented, but the living memory of decisions made 4 decades earlier, and the perspective that comes only from having watched the mission evolve across its entire arc. The day-to-day operation of Voyager 1 today falls to a small team at JPL. Dozens of scientists and engineers, rather than the hundreds who staff the planetary encounter phases. They communicate with an instrument they cannot inspect, cannot touch, cannot repair in person, and can only interact with through signal exchanges in which each round trip takes 46 hours. When something goes wrong aboard Voyager 1, the team does not learn about it for 23 hours. When they send a corrective command, it takes another 23 hours to arrive. The entire process of diagnosing an anomaly, formulating a response, transmitting it, and receiving confirmation plays out over timescales of days. Every command must be carefully analysed before transmission because there is no opportunity for real-time correction once the signal is in transit. The experience of operating Voyager 1 today defies the ordinary intuitions about communication that govern every other professional interaction its team members have. When a command is composed, reviewed, approved and transmitted from JPL, the signal leaves the 70-metre antenna at the speed of light and travels outward, across 15 billion miles for 23 hours before reaching the spacecraft. If the command produces a response, a health status readback, a confirmation of execution, new science data, that response travels back at the speed of light for another 23 hours before arriving at Earth. 46 hours for a single round-trip exchange. Nothing in modern human experience prepares people for communication on this time scale. Email responses that take hours feel slow. A text message that takes more than a few minutes raises concern. The Voyager team plans, reviews and transmits commands knowing they will not know whether those commands were successfully executed until the following day. This requires a specific discipline. Commands must be simulated and verified with extraordinary care before transmission, because there is no opportunity to catch an error once the signal is in transit, and no way to interrupt a command sequence that has begun executing at the spacecraft before its next step is already underway. The team has developed this discipline across nearly 5 decades of operation, building institutional habits for deliberate slowness and systematic verification that are the direct consequence of communicating across a distance where light itself takes nearly a day to traverse. This constraint nearly ended the mission in late 2023. Voyager 1 began returning garbled telemetry, data streams that the ground stations could not pass into meaningful information. The corruption was systematic rather than random, structured in a way that was reproducible and eventually diagnosable, but initially completely incomprehensible. The engineering team spent several months methodically investigating the problem from 15 billion miles away, with only the corrupted data itself as evidence from which to deduce the cause. They determined that a chip in the flight data system and the component responsible for packaging data into the formatted stream used for transmission had developed a fault that caused it to write data to a non-functional memory location, corrupting the output in a consistent but initially mysterious way. The fix required creative engineering that no operational manual had anticipated. The team developed a workaround that redistributed the affected data across other available memory locations, routing around the faulty chip without physically replacing or modifying it. The commands implementing this workaround were transmitted to Voyager 1 in April 2024. 23 hours later, the spacecraft responded. The next telemetry downlink arrived with clean, readable data for the first time in months. From 15 billion miles away, using only transmitted software commands as their only interface to the physical reality of the machine, a team of engineers had diagnosed and repaired a hardware fault in a 47-year-old spacecraft operating in interstellar space. It is one of the most extraordinary acts of remote engineering in human history, conducted across a communication delay that made every step feel like sending a message into the dark and waiting an entire day to learn whether it had worked. The emotional dimension of this mission is real and deserves direct acknowledgement. There is something that functions as genuine attachment in the relationship between this team and this spacecraft. A connection to a machine that has been in continuous operation since before many current team members were born, that has travelled farther from Earth than any other human-made object, and that continues returning data from a position in space no other instrument occupies. When the telemetry went dark in late 23, the people who have devoted years of their professional lives to this mission did not respond as if a piece of equipment had malfunctioned and required repair. They responded the way people respond when they lose contact with something they care about. The relief when clean telemetry returned in April 2024 was, by multiple accounts, profound. Not simply the professional satisfaction of a solved technical problem, but something closer to what you feel when a long silence finally breaks. When the garbled telemetry began arriving in late 2023, the experience for the mission team was not the clean frustration of a straightforward technical failure with a known cause. It was the specific disorientation of receiving a signal that was clearly present. The carrier frequency was strong, confirming the transmitter was running and the spacecraft was operating, but carrying data that could not be read. Something that had been intelligible for 46 years was suddenly speaking in a language that no one on Earth could parse. The team faced a diagnostic challenge with no precedent, determining the cause of a systematic hardware failure in a 47-year-old spacecraft using only the corrupted output of the failed component as evidence, with no ability to physically inspect anything, and with each diagnostic test requiring a minimum of 46 hours to yield any result. The months that followed required the team to sustain a productive scientific and engineering posture, while their primary data connection remained broken, to keep monitoring the signal for clues, to model possible failure modes, to design and propose remedies that could be implemented purely through transmitted software commands, and to maintain the institutional coherence needed to see a months-long diagnostic process through, without the reassurance of incremental visible progress. This kind of patient technical composure under conditions of sustained uncertainty and remoteness, staying systematically productive when nothing you try produces immediate feedback, has no close analogue in any other field of engineering practice. This is not anthropomorphism, it is recognition of something genuine. Voyager 1 carries with it not just instruments and data, but the evidence of a decision made at a particular moment in human history. The decision to send something outward, beyond the known, without certainty about what would be found, without assurance of survival, and certainly without knowing that nearly 50 years later it would still be out there, still transmitting, still finding things the universe had not yet been asked about. The spacecraft is human curiosity made physical, a piece of our best impulses launched into the permanent dark and still faithful to the work it was sent to do. The power decline continues regardless of sentiment. Each year the RTGs produce roughly 4 fewer watts than the year before. The instruments require minimum power thresholds to function, fall below the threshold for any given instrument, and it must be shut down permanently. Not because it has failed, not because its science is no longer valuable, because there is not enough electricity to run it. Each shutdown closes a window of observation that will not reopen. Current projections suggest that the last active science instrument will need to be shut down sometime around 2025 or 26. After that, the spacecraft may continue transmitting engineering data, for some additional period, but it will no longer be doing science. The solar system's only active observer in interstellar space will have gone silent. The triage decisions imposed by declining power have followed a logic that evolved as the mission's understanding of its own constraints matured. Early shutdowns targeted systems with high power draws whose primary scientific work had already been completed. The imaging system and its scan platform consumed significant power and required heaters to prevent lubricant from freezing in the outer heliosphere. After the pale blue dot family portrait in 1990, there were no more planets to photograph, and their power was freed for instruments still actively measuring the environment. The plasma subsystem's heaters were cut years before the subsystem itself was turned off, accepting a calculated risk of cold-induced failure in exchange for the watts needed to keep higher priority instruments running, a decision requiring the team to estimate whether the instrument would survive the cold long enough to justify the power saving, knowing the estimate might be wrong and the instrument might fail earlier than projected. Each of these decisions was made with full awareness of its irreversibility. An instrument powered down in the minus 270-degree interstellar environment cannot simply be restarted if the team later decides the power budget could accommodate it after all. The team had to develop a specific tolerance for irreversible commitment, the ability to permanently sacrifice something of value now in order to preserve something of greater value for an uncertain future, without the psychological safety net of being able to change the decision if circumstances changed. Even after the instruments go dark, Voyager 1 will not stop. It will continue travelling at 38,000 miles per hour for millions of years, unless it collides with something, vanishingly unlikely in the vast emptiness of interstellar space. In approximately 40,000 years, it will pass within about 1.6 light-years of a red dwarf called Gliese, 445 in the constellation Camelopardalis. The closest any human-made object will come to another star in the foreseeable future, a moment that will unfold on a timescale that dwarfs the entire span of recorded human civilization by a factor of more than 10. The physical reality of Voyager 1's future trajectory is governed entirely by Newton's first law applied to an object moving through a medium so sparse that its resistance is effectively zero. Without any significant gravitational body to deflect it, the spacecraft will continue on its current heading at its current velocity, essentially unchanged for periods that challenge any ordinary intuition about time. In approximately 300 years, it will reach the inner edge of the Oort cloud, the vast, diffuse shell of cometary bodies that surrounds the solar system at distances of 2,000 to 100,000 astronomical units, too distant to have ever been directly observed. It will take tens of thousands of years to traverse this region. In approximately 40,000 years, it will pass within about 1.6 light-years of the red dwarf star Gliese, 445 in the constellation Camelopardalis. Not close enough to be captured gravitationally, but the nearest any human artifact will come to another stellar system in any foreseeable future. These timescales make the 5-decade mission that will soon be complete seem like a brief prelude to a journey that has barely begun. Every civilization that exists on Earth today will be unrecognizable before Voyager 1 reaches its nearest stellar neighbor. Every language in which human beings currently communicate will have evolved beyond recognition or gone extinct. The spacecraft will carry its record of our existence into a future in which no one alive today has any meaningful stake and which exceeds every human timescale by orders of magnitude. Attached to the exterior of Voyager 1, protected by an aluminum cover designed to resist interstellar dust over geological timescales, is the Golden Record, a gold-plated copper disc containing 116 images encoded in analog form, greetings in 55 human languages, a 90-minute selection of music spanning Bach and Beethoven and Chuck Berry, and traditional music from every inhabited continent. Sounds of Earth including wind, rain, surf, thunder, birds, frogs, whales, and a human heartbeat, and scientific information including pulsar timing data that locates Earth's position in the galaxy. It also contains encoded brainwave recordings made by Andrew Yan, Carl Sagan's future wife, while she thought about the history of Earth and the meaning of love. The record was assembled in roughly 6 weeks under the pressure of a non-negotiable launch deadline by people who had no idea whether anything would ever receive it. The golden record will outlast every city, every monument, every civilization, every biological descendant of every person alive today. In the timescales relevant to stellar evolution, it will outlast the sun itself. It is the most far-flung artifact of human culture in existence, moving farther from Earth every second of every day, carrying into the permanent dark a record of the species that built the spacecraft it rides. Whether any intelligence will ever find it is one of the most profound open questions imaginable. But it was sent regardless, because the people who made it believed the attempt was worth making, even without any assurance of success or any prospect of a reply. That choice, to reach out into a silence that might be total and permanent, says something important about what humanity is capable of when operating at its best. The contents of the golden record were assembled under the specific constraint of a deadline that could not move, producing choices that were necessarily hasty by the standards of any cultural institution operating with normal timescales for deliberation. Carl Sagan chaired the committee, working with Andrew Yan, who would become his wife, Frank Drake, who had designed the first systematic search for extraterrestrial radio signals, and colleagues from multiple disciplines who were each prepared to argue vigorously for the inclusion of specific content. The 116 images were encoded in analog form using a visual format explained on the record's cover. DNA structure diagrams, human anatomy, Earth's geography, the solar system, mathematical constants, images of humans engaged in daily activities across multiple cultures. The 90-minute audio section includes greetings spoken by the United Nations Secretary-General and children, spoken greetings in 55 human languages, ranging from Akkadian to Wu Chinese, a 12-minute collection of sounds from Earth, wind in trees, rain, surf, thunder, the calls of birds and humpback whales and frogs, human laughter, a mother and child, and 55 minutes of music spanning Bach's Brandenburg Concerto, Beethoven's Cavatina, Louis Armstrong's Melancholy Blues, Chuck Berry's Johnny B. Good, and traditional music from Indonesia, Senegal, Azerbaijan, the Solomon Islands, Peru, Bulgaria, and 8 other nations. Andrew Yan's brainwave recordings, made during a meditation in which he consciously thought about the history of Earth and the feeling of love, were included on the record itself, a deeply personal contribution to a message designed for an audience that does not yet exist. This is what makes the approaching silence of Voyager 1's instruments something more than the end of a scientific program. When the last instrument goes dark, something genuinely unprecedented will have ended. Humanity will have sent an ambassador to interstellar space, kept it alive through nearly 50 years of patient operation and ingenious management, extracted science from it that no other means could have provided, and watched it go silent while still travelling outward, still carrying its record. The science will continue beyond the silence. The papers being written right now, analysing the plasma oscillation data and the cosmic ray spectra and the magnetic field measurements from the spacecraft's current position, will continue generating publications and revisions to theoretical models for years after the instruments stop functioning. Scientific knowledge produced by Voyager 1 will outlast Voyager 1's active operation, just as the light from distant stars continues reaching our eyes long after those stars have consumed their fuel. The end of active data collection will not end the scientific work that Voyager 1's nearly 50-year mission has made possible. Data archives from space missions have routinely continued generating scientific publications for decades after the instruments that produced them went silent. Pioneer data, Voyager planetary encounter data, Mariner data, all continue to be reanalyzed as new theoretical frameworks and new computational tools allow researchers to ask questions of old data sets that were not formulated when the data was first collected. The Voyager 1 Interstellar dataset, when complete, will contain something no prior archive has ever held: a sequential record of direct in situ measurements of the near-interstellar medium at progressively increasing distances from the heliopause, spanning more than a decade of continuous observation. Every future model of the heliosphere's outer boundary and the near-interstellar medium must either be consistent with this record or specifically account for why it should differ. Theoretical papers that cite Voyager 1 interstellar data are already appearing years after the most significant findings were first published, as researchers find new ways to interpret the existing measurements in light of updated theoretical frameworks. This will continue after the instruments go dark. For as long as heliospheric physics remains an active field, which is to say, for as long as we remain interested in understanding the boundaries of the domain in which our solar system exists, there will not be another Voyager 1. This requires careful explanation because it can sound pessimistic about human ambition. It is not pessimism, it is a statement about physics, geometry, and time. The planetary alignment that Gary Flandreau identified in '65, the Grand Tour window that made it possible to send a single spacecraft past all 4 outer planets using sequential gravity assists, closed in the early 1980s. The next comparable alignment will not occur until the year 2153. A mission reaching the heliopause via a direct trajectory would require either a substantially faster spacecraft than anything currently available, or a transit time of several decades. The fastest direct trajectory achievable with current propulsion technology would require 30 or more years to reach the heliopause, meaning any mission funded and launched today would not begin returning interstellar science data until well into the 2060s at the earliest. The year 2153 is not an abstraction. It is a specific date whose distance from the present moment is comparable to the distance from the American Civil War to today. In the span from 1863 to now, the United States went from horse-drawn transportation to the moon landing, from the telegraph to the global internet, from a population of 30 million to more than 300 million, from no conception of the germ theory of disease to the mRNA vaccine. The technological civilization of 2153 will bear some relationship to the civilization of today, but predicting its specific character is impossible, in the same way that predicting the internet would have been impossible to someone standing in the Civil War era. What is certain is that the orbital geometry will be available, the same gravitational clockwork of the outer solar system ticking steadily toward the next Grand Tour alignment, the same Jovian and Saturnian and Uranian and Neptunian masses orbiting in their slow ellipses according to the same laws of motion that Gary Flandreau used in 1965. Whether any civilization that exists in 2153 will choose to use that window, whether anything resembling a modern space agency will be operating, whether the concept of a grand robotic emissary sent to the outer solar system at a specific moment of orbital opportunity will still be a meaningful framework for organized human action. These are not questions anyone alive today can answer. The universe does not promise that windows will be used, it only promises they will open. A successor mission has been proposed and studied seriously within the planetary science community for more than 2 decades. NASA's Interstellar probe concept envisions a spacecraft designed specifically for interstellar science, equipped with modern instruments of vastly greater sensitivity than Voyager 1's 1970s technology, launched on a faster trajectory using a solar gravity assist, capable of reaching the heliopause in roughly 15 years rather than 35. Such a spacecraft would arrive with instruments designed for the job rather than adapted from a planetary mission, and it would benefit from everything Voyager 1 has already taught us about what the interstellar medium contains. But funding has not been secured. Until it is, and until any such mission actually reaches the heliopause, Voyager 1 remains the only active instrument in interstellar space. That singularity defines the mission's importance right now, not historically, not symbolically, but scientifically in the most direct, practical sense. The measurements from Voyager 1 are not merely interesting among many competing datasets, they are the only measurements. The plasma density values it reports, the cosmic ray fluxes it measures, the magnetic field directions it records. These are the only direct data points humanity possesses for the local interstellar medium. Every theoretical model of the heliopause and the interstellar environment must either be consistent with Voyager 1's data or specifically account for why it should differ. In a field where theorists have worked for decades without experimental constraints from the actual location of interest, those measurements carry weight that cannot be overstated. There is a concept in science called ground truth, a direct measurement taken at the location being studied, rather than a remote measurement inferred through models. For the local interstellar medium, Voyager 1 is the only ground truth that exists. Everything else is inferred. The ground truth is 15 billion miles away, returning signals at 22 watts, captured by dish antennas in the California desert, the plains of Spain, and the Australian outback, and the ground truth is still running. That is the answer to the question this story asked at the beginning. What is Voyager 1 still discovering in interstellar space? It is discovering that the local interstellar medium has physics of its own, structure, dynamics, and measurable properties that older models did not capture. It is discovering that the boundary between the heliosphere and interstellar space is a dynamic, complex interface that continues to influence the surrounding medium well beyond where the sun's direct particle wind ends. It is discovering that the plasma between the stars resonates and responds to solar activity transmitted through the heliopause, exhibiting density variations that reflect processes ranging from individual solar events to the large-scale structure of the galactic neighborhood. It is discovering that the cosmic rays streaming through this region carry a specific energy distribution that reflects both the filtering effect of our heliosphere and the character of the local galactic environment. It is discovering that interstellar space is not featureless darkness between the known and the unknown. It is a region with character, measurable, comprehensible, worth understanding, and the first instrument to reach it is running out of power. The scientific legacy of Voyager 1's interstellar observations can be partially expressed in specific measured quantities that did not exist before the spacecraft reached interstellar space. The electron density in the local interstellar medium just beyond the heliopause, approximately 0.8 electrons per cubic centimeter, a value that constrains theoretical models of the local bubble's plasma properties in a way that only direct measurement can provide. The strength of the magnetic field in the interstellar medium, approximately 0.5 nanoteslas, weaker than even the already faint fields of the outer Helios heath, providing the first direct measurement of the galactic field at this specific location, rather than an inference from more distant observations. The factor of increase in galactic cosmic ray flux upon crossing the heliopause, roughly 2 to 3 times the Helios sheath levels, with an energy-dependent pattern that reveals how the heliosphere modulates different particle populations to different degrees. The temperature of the interstellar plasma derived from the oscillation measurements, approximately 30,000 to 50,000 Kelvin, hotter than simpler models had assumed, a constraint that changes the physical picture of the state of the gas between the stars in our local galactic neighborhood. Each of these numbers looks unremarkable on a page. Each represents a fact about the universe that was unknown to all of human history before Voyager 1 measured it. The compactness of the expression conceals the depth of the ignorance it replaced. Stand outside on a clear night, look up, find a star. The light reaching your eyes left that star years, decades, or centuries ago, and it crossed the same kind of space that Voyager 1 is moving through right now, the same sparse plasma, the same ambient cosmic ray flux, the same magnetic field threading through the space between the stars. Every time you have looked at the night sky in your life, you have been receiving light that travelled through interstellar space to reach you. The light has always been there. The measurements from inside that space, direct observations taken from an instrument physically located within the interstellar medium, have never existed before. Voyager 1 created that ground truth. While the instruments last, it continues to add to it. Right now, as you absorb what that means, a small machine built by human hands in the early 1970s, smaller than a compact car powered by less than a refrigerator bulb, is moving through the space between the stars at 38,000 miles per hour. Its transmitter is running. Its remaining instruments are collecting measurements from a location in the galaxy that no other instrument has ever sampled. The data those instruments are generating is travelling toward Earth at the speed of light, taking 23 hours to cross 15 billion miles, spreading across an ever larger sphere of space as it travels, growing weaker with every mile until it reaches the enormous dish antennas listening for it in 3 locations around the rotating Earth. The physical act of receiving Voyager 1's signal at Earth's surface is as extraordinary as the signal's journey across 15 billion miles. The 70-meter dish antenna at Goldstone in California's Mojave Desert, one of the 3 primary stations of the Deep Space Network, rotates to track Voyager 1's position as Earth turns, gathering electromagnetic energy with a collecting area of nearly 4,000 square meters and focusing it onto a receiver cooled to within a few degrees of absolute zero to eliminate thermal noise from the detection process. The signal arriving after 23 hours of travel has been attenuated by a factor approaching 10 billion, a number requiring 18 zeros after the 1, by the inverse square spreading of the electromagnetic wave across 15 billion miles. The receiver electronics, developed through decades of refinement specifically for this application, extract a coherent signal from noise levels that would defeat any commercial radio system. The data stream that emerges from this process, carrying the latest measurements from Voyager 1's active instruments, is transmitted to JPL in Pasadena for decoding, calibration, and distribution to the relevant science teams. The entire chain, from 22 watts of transmitter power at 15 billion miles to a few dozen kilobytes per day of science data at a JPL workstation, is a technical achievement of the first order, maintained continuously for nearly 50 years by the operations teams of the Deep Space Network. 23 hours from now, that signal will arrive. Engineers will receive it, process it, and add the latest measurements to the record. The record will be analysed, debated, published, and incorporated into the growing body of what humanity knows about the universe outside the solar system. And somewhere in the data arriving at that antenna will be the latest measurement of what the interstellar medium is actually like at Voyager 1's current position, a measurement that exists nowhere else in the world, produced by a machine that should have gone dark in the early 1980s, still faithfully performing the work it was sent to do. When the Deep Space Network antennas receive Voyager 1's signal, the raw data stream is processed, decoded, and distributed to the science instrument teams within hours. The process of analysing what arrives is quiet and methodical, ordinary scientific practice but conducted at a unique remove from the phenomena being observed. A plasma wave scientist reviewing the latest oscillation data looks for signs of a new pressure wave arriving from the Sun, comparing the current readings against the history of previous oscillations, checking for frequency shifts that would indicate a changing plasma density, correlating the timing against databases of solar energetic particle events from months or years earlier that might have generated the triggering disturbance. A cosmic ray physicist examines the latest particle energy spectra for gradual shifts in flux or composition that might signal the spacecraft's movement into progressively less disturbed interstellar medium, farther from the heliopause. The magnetometer team tracks slow variations in field direction and strength, asking whether each change reflects genuine spatial structure in the interstellar medium or instrument noise or attitude fluctuations in the spacecraft. When accumulated data supports a conclusion, when a pattern is clear enough, a physical interpretation robust enough, a dataset large enough to warrant reporting to the broader scientific community, a paper is written, submitted to a journal, reviewed by peers, and published. The daily rhythm of this work produces no dramatic moments. It produces the slow, incremental, irreplaceable accumulation of facts about the universe that no other source can provide. The final instrument will shut down on a day the team is already working to push as far into the future as the physics of radioactive decay permits. When that day comes, humanity will have done something that deserves to be remembered clearly. We built something small enough to fit in a parking space. We launched it nearly 50 years ago on the narrowest of orbital windows, with technology we would now call primitive. We guided it past the 4 great planets of the outer solar system, used their gravity to fling it onward, and watched it cross the boundary into a region of space where nothing we had ever made had gone before. We kept it alive through 5 decades of patient engineering and careful management. We fixed it from 15 billion miles away when it broke, and we listened to everything it had to say for as long as it could speak. The signal is on its way. It will be here tomorrow, and every reading it carries is one more piece of the universe we have never had before.